Welcome to the AI Research Roundup. I'm Alex. Today, we're exploring navigation world models from December 4th, 2024. This paper introduces the Navigation World Model, or NWM. Essentially, this Navigation World Model is an AI that predicts future sites for an agent, like a robot, based on past views and actions, by generating video. To do this, the Navigation World Model uses a Conditional Diffusion Transformer, or CDIT. This Conditional Diffusion Transformer is a sophisticated AI, trained on many first-person videos, enabling the system to plan routes and even imagine paths in new places from a single image. Alright, and for those of you who want to get hands-on with this, the authors have actually released the official PyTorch implementation of their work. PyTorch, by the way, is a popular open-source library used for building and training machine learning models. So on GitHub, you can find all the code for their Conditional Diffusion Transformer model, including training scripts, evaluation tools, and even an interactive notebook to experiment with. Alright, so Figure 1 really helps us see this Navigation World Model in action. Part A illustrates the core idea. The model takes a current view, which is first processed by something called a variational autoencoder, or VAE. A variational autoencoder essentially compresses the image into a simpler numerical representation, or code. Then, along with navigation instructions, like how far to move, turn, and over what time, the Conditional Diffusion Transformer predicts the code for the next view. This code is then decoded by the variational autoencoder back into an image. Part B then shows this system generating future video frames to evaluate a planned path, checking if the end lines up with a goal. And Part C, well, that showcases it imagining trajectories in new places from just one initial image. Figure 2 now takes us deeper into the Conditional Diffusion Transformer, showing one of its core processing blocks. This block efficiently handles the encoded future frame. It uses multi-head self-attention to analyze features within that upcoming frame. Then, alright, so now that we've peeked inside a processing block of the Conditional Diffusion Transformer, Figure 3 shows us some qualitative examples of the Navigation World Model in action. We're looking at generated video frames as the model follows ground truth trajectories. These ground truth trajectories are just the actual recorded paths taken in these different known environments. So environments the model has likely learned about. These visuals, then, demonstrate how well the Navigation World Model can predict and reconstruct the sequence of sites, as if it were moving along those predefined paths in these familiar settings, from outdoor scenes to indoor corridors. Alright, so we've seen how the Navigation World Model visualizes paths. Figure 4 now quantifies this prediction quality, comparing it directly against another method called Diamond, using the Recon dataset. The graphs tracked two key scores over time. First, Fréchet inception distance, which assesses the realism of the generated video frames. A lower score here means more realistic. Second is learned perceptual image patch similarity. This measures visual similarity between the prediction and the actual view, and again, lower indicates a closer match. The Navigation World Model consistently shows lower, and thus better, scores for both Fréchet inception distance and learned perceptual image patch similarity, outperforming Diamond as predictions extend further in time. Okay, so after seeing how the Navigation World Model stacks up against other methods in Figure 4, Table 1 now gives us a closer look at how different design choices within the model itself affect its prediction accuracy. This is an ablation study, where researchers tweak parts of the model to see what really matters. The table uses learned perceptual image patch similarity, which we've discussed, and also DreamSim, another visual similarity score where lower is better, plus peak signal-to-noise ratio, or PSNR, where a higher value indicates better image quality. The results show that using more goal samples and more context frames both improve predictions. Importantly, conditioning the model on both action and time information together leads to the best performance by a significant margin. Alright, so building on those internal model comparisons from Table 1, Figure 5 really showcases the efficiency of the Conditional Diffusion Transformer, the core of our Navigation World Model. It plots prediction accuracy using learned perceptual image patch similarity where lower is better against computational cost and teraflops, which are terafloating point operations per second, a measure of processing needed. The blue conditional diffusion transformer models achieve better accuracy for less computation than the red standard ones. Then, Figure 6, the table below, compares video synthesis quality using Fréchet video distance, or FVD, a metric for video realism where lower is better. The navigation world model shows a dramatically better Fréchet video distance than the diamond method, highlighting its superior video generation. Okay, so after seeing the navigation world model's strong video synthesis in Figure 6, Figure 7 demonstrates a really practical application of its predictive abilities. Here, the navigation world model is used to rank different paths or trajectories that are suggested by an external navigation policy. You can see an initial observation view and a goal image. The model then simulates several potential paths, P1, P2, and P3, predicting the final view for each. It then scores how well each predicted final view matches the actual goal image, using a loss value where lower is better. This allows the navigation world model to pick the most promising path, in this case, P3. As we saw with that path selection in Figure 7, this navigation world model really excels at understanding and predicting complex scenarios. The key takeaway is the power of its conditional diffusion transformer architecture for efficient, high-quality video prediction, which directly helps in planning. This is a big step for creating more intelligent agents that can navigate our world. Thanks for tuning in to the AI Research Roundup. I'm Alex.